During this session, I'm going to discuss the states of matter, specifically trying to use some of the language which is really important to emphasize when describing it at both a macroscopic level and a microscopic level. So let's start off what you should probably already know about. The three states of matter which we're familiar with on planet Earth would be solid, liquid and gas. And macroscopically, a solid is known to hold a fixed shape and also have a fixed volume. Liquids will take the shape of the container. They have a free surface, but they also have a fixed volume. They're unable to compress these much further. And finally, we have gases. And gases are known to take the shape of the container. If we blow a balloon up, they'll take the shape of the balloon. And they will always just meet the volume of the container. So they'll stretch out and take over the whole volume of the container we have. So these are the macroscopic properties. What we need to think about is states of matter microscopically as well. And in this feature, the best way to explain it is by thinking of the model of them, all states of matter being made up of specific molecules. Now, these molecules help us describe and explain both the properties at a macroscopic level, and it also really helps us get to grips of why these properties take place. They're also crucial in understanding and describing the microscopic properties. So as we see in this diagram, we have solids. Solids have a fixed structure where all the particles are closely linked together and then able to move any further. As we heat things up, solids transform into liquids. In liquids, there's still a force between the particles, but this force doesn't keep them in a locked position. They're able to move around and shift shape, so they can change shape very easily, but their volume is pretty much constrained by how much volume these particles take up. Then if we think about a gas, in a gas these particles are free to move around, and that forces holding the liquids together have been broken to allow gases to take place. In the wider universe, we also have the state of plasma. Plasma is a state of high extreme temperatures and pressure where the atom itself has started to break down, and that's not something I'm going to talk about in much detail for now because it's not required. So with these states of matter, as we can see, as we change temperature, let's say we had a solid and we heated it up, then what would happen as it heats up, the solid would change into a liquid. So this would be at the melting point. That requires some energy, so the energy doesn't change. The temperature doesn't change while this change of state is taking place, and we'll come back to that later in the course. And then the liquid will have an increase in temperature until it reaches that point, the boiling point, where the liquid can change state into the gas. And the gas will continue to increase temperature. Now let's think about the microscopic characteristics. Okay. First of all, I'm going to start off with a gas. Gases, the kinetic energy of these particles means that these particles can move around, they can translate. So there's lots of translation energy. The kinetic energy, these particles can also rotate around a lot, and they can also vibrate a lot. So that's where the kinetic energy is. And the potential energy, which is the energy of these particles being a long way away from each other, is at its highest. For a liquid, they can continue to vibrate, and they can also have the freedom to rotate. And there's some translational energy, which means that this kinetic energy means they can move around a little bit. The potential energy is higher than that of a solid, because they can be further apart. The potential energy between particles is slightly higher, but less than that of a gas. A solid only has vibrational kinetic energy. It can only vibrate and nothing else. There is still some potential energy between them due to the forces between these particles, but this is the lowest of the three states. It's important to recognize the correct names for these changes of state. A change of state which you'll probably come off most rarely is that of sublimation. Subliming is when a particle, a matter, changes directly from solid to gas. Going from a solid to a liquid, we have melting, and from a liquid to a solid, we have freezing or solidifying. From a liquid to a gas, we have boiling or vaporizing or evaporating. And these have all got slightly different terms, which I'm going to explain briefly later on. A gas can condense or liquefy as it turns from a gas to a liquid. Now, I mentioned there's a distinction between evaporation and boiling. So let's just set up ourselves as a picture in our head of imagining arriving at school and there's a puddle of water on the ground because it's rained. Now, when you come back out of school again, these puddles are generally gone. The water in the puddle has evaporated. It certainly hasn't boiled. You'd be well aware if the temperature of your playground had gone above boiling point of water. So let's just make this distinction and kind of explain why these two things are different. So, the reason why these two things are different, first of all, we need to think about what temperature really is. Now, temperature talks about the average kinetic energy of particles within that matter. And average means that not every single particle is going to have that amount of energy. There's going to be a whole spread of different energies. Some particles are going to have very little energy, some particles are going to have lots of energy. And it's those particles which have lots of energy which we're interested in. Because some of those particles are going to have enough energy that it's going to be greater than the normal boiling point. They're going to have enough energy to break away from this liquid. And that's exactly what we do. We find that these particles, or this number of particles which have more energy than that, they will evaporate because they have enough energy to break with the bonds of the liquid. Now this is quite an interesting thing because when they evaporate, what happens is we lose some particles at that end. And by losing those particles, it means that the average kinetic energy shifts a little bit. With those faster moving particles, the average kinetic energy shifts. So overall, there's been a cooling of this process. And this is known as evaporative cooling.